Hi to everyone. Welcome to this webinar on measurement technology for hydrodynamics applications. My name is Pascal Erne and I'm application engineer at Kistler. Please be aware that you're muted per purpose and that this webinar is recorded. So we will share the recording after the webinar so that you can rewatch it on your own pace. If you have any questions, please feel free to ask them in the Q&A section on the right-hand side. And now let me introduce Bill Zwolinski. Bill is our application engineer in test and measurement for America and has an enormous background. He's not only working for Kistler for more than 20 years, he holds also a master's degree in electrical engineering, specializing in signal processing and controls. He has worked in the field of underwater acoustic and has been chief engineer for the Navy carrier landing system at Textron. With this extensive know-how in both the mechanical and electrical world, he's heavily involved in solving our customers' measurement problems. And now I would like to hand over to you, Bill.
Thank you, Pascal. Appreciate the introduction. Okay, so let's proceed here. So what I'm going to do today is basically present a brief introduction. Okay, we're going to talk a bit on piezoelectric principles of operation, what typical measuring chains might look like, talk about force and pressure and acceleration measurement and some applications, of course, and then obviously a summary and wrap up, and hopefully I get a few questions and at the end, and that would be really great to hear any feedback or any questions from your side. So in hydrodynamics anyway, you know, when we talk about technologies, I always think about physical measurements, okay? Because really what you're thinking of here is in hydrodynamic testing, you're thinking about how liquids in motion affect ships and coastal structures, how they affect structures indeed, you know? So there's many ways to go about that for sure. From an R&D perspective, certainly tow tanks, wave tanks, water tunnels, sloshing rigs, and so forth are all quite available and very good resource to be able to test various concepts and designs. So, you know, from that, there's quite a few applications, of course, you know, from reaction forces and moments to seakeeping tests to ship maneuverability and stability, wave impacts and how waves affect structures, and certainly how flow induces structures as well with vibration and load. So there's quite a broad field for sure, but what we're going to talk today is about, you know, how do we make the physical measurements and what technology should we consider? So just to start this off, we're going to go and talk a bit about piezoelectric instrumentation. And with piezoelectric instrumentation, we'll address force, pressure, and acceleration. With force sensors, I mean, with all this technology, you're primarily using quartz as the piezoelectric material. And what happens is you can form that quartz or cut it in certain ways to achieve the measurement. For example, in force, you would want the quartz cut in a compressive manner to measure Fz, and to measure X and Y, you'd want it to cut in a way that it can measure shear forces. So you can easily do that for sure. In pressure, more along the same concept where you can cut the quartz for optimizing pressure measurement, and certainly in acceleration. Nowadays, shear cut quartz or piezoelectric materials are more or less prominent. They are absolutely the best performing for acceleration as well. So in terms of piezoelectric, there's some terminology, of course. There's always terminology associated with various technologies. So PE means basically there's no electronics in the sensor, where IEPE means integrated electronics piezoelectric. And that's when there's an electronics inside the sensor. So what advantages or what could be the takeaways from this? Well, piezoelectrics, you basically have a very wide measuring range, but you're quite rangeable. There's an external charge amplifier which converts the charge signal, the electrical charge signal from the sensor to a voltage, and that voltage can be used in a data acquisition system. You can also use it in a quasi-static manner, the piezoelectric solutions. By having the right charge amp, you can optimize on the low frequency measurement. You could also reset and tear, reset and measure and tear the measurement as well. If you had, 1,000 pounds of mass acting upon a force sensor, you can basically tear that out. So electrically, you don't have to deal with the mass, but obviously, mechanically, the mass is there. But electrically, your measuring chain can look at the dynamics that are happening with that mass, rather than the mass plus the dynamics. With IEPE, it's basically your fixed range, okay? There's electronics inside the sensor, which means that you're fixed in range. You can't range it. It's really for only dynamic measurement, so it has a very limited view, but it's still quite useful. I'd say acceleration is one of the areas that, and vibration are one of the key areas that use IEPE, and there is some pressure and force, of course, but acceleration or vibration would be the key application or key measurand for that. So with piezoelectric devices, I always like to think about what the frequency response is. And what it is really can be modeled by a first order high pass characteristic on the low end with a lightly damped second order characteristic on the high end. So what that means is basically you're going to have a resonance in the sensor. It's lightly damped, so it will exhibit some peaking, certainly out in frequency. A lot of times this peaking is well out there in frequency, so it really doesn't affect the measurement, and you can simply filter it out if you see any frequencies at that range. But one of the nice things about using that lightly damped second order model is that you can derive closed form expressions as to what the amplitude response tolerances could be. For example, the 5% amplitude response tolerance would be Fn over 5. That's the natural frequency over 5. So if you had a system with a 1 kilohertz natural frequency, you would expect a 5% frequency of about 200 hertz. And you could apply the same type of strategy to a 10% or even a 3 dB by virtue of Fn over 3 or Fn over 2. So what happens is that by using those rules, you can now set the amplitude response tolerance band accordingly so that you can measure the frequency range of interest. On the low end, like I mentioned before, it's a single order high pass characteristic, and this looks like an incredibly busy chart, but there's a lot of information on it. What I try to do is really derive from a Laplace domain related expression on the high pass filter what the actual 5%, 10%, and 3 dB closed form expressions would be, and you can see those on the left hand side. What happens in charge amplifiers is that the basic time constant or the low frequency characteristic of the amplifier is effectively related to the measuring range that you've selected. That's not uncommon, okay, in charge amplifiers. And I just show you an example here where if you have, let's say, a 3-second time constant, that would relate to, say, a 0.16 hertz 5% frequency on the low end. So when you do get into piezoelectric measuring chains with charge amps, it's often good to understand what your low frequency requirements are, as well as the high frequency requirements. Okay, provided in the last slide, your high frequency will be related to the natural frequency, whereas your low frequency is going to be related to the time constant of the amplifier. So there's more terminology, quasi-static and dynamic. Well, there are amplifiers that just measure dynamic only, okay? A lot of times those are used in vibration analysis, vibration measurement, and they're very, very useful, very much rangeable, all the features that I talked about previously. Then there's a special class of amplifier that's both quasi-static and dynamic, which means that it can measure the low frequency characteristic as well as the high frequency. And what that does is it allows you to now use quartz technology that you can optimize on a quasi-static solution in addition to the dynamic. Of course, selecting the right charge amplifier will be very important to what you're trying to measure in terms of, is it a short-term transient? Is it a random event? Is it a static event, a static force event, and so forth? Those are all quite critical when you make those decisions. In any piezoelectric measurement, you're going to have, when you're in a quasi-static mode, when you're trying to optimize on the low frequencies, there's a drift component, and this is an attribute of the amplifier itself. And it's quite low, okay? It's a quite low figure, but when you're measuring high forces, a lot of times it's very much negligible. Okay, but when you're trying to measure very low forces, quasi-statically, it can be a sizable amount. So you always have to look at this in terms of your application and find out what the best way to measure it. And certainly, quasi-static measurement is very popular with piezoelectric, and certainly it's related, but basically by the sensitivity of the sensor. The higher the sensitivity of the sensor, the lower the drift. So there's a technology called PiezoStar, which is optimized for sensitivity, and it's 3 times the sensitivity of quartz, and it's indeed gives you 3 times less drift as quartz. So it's very good for that in terms of a quasi-static measurement. Like I mentioned, low forces, very low forces in quasi-static, typically you don't do, but there are reasons and there are rationale behind when you can do it. And certainly consult your favorite application engineer to brainstorm on that. And certainly, roughly, if you're doing force measurement, I mean, a drift, on a traditional quartz sensor would be something on the order of 1/10 of a pound per minute or 1/2 a Newton per minute. If you're using PiezoStar, it's going to be 1/3 of that. So it's quite low indeed. So the other thing I mentioned before is with PE measuring chains is rangeability, and by using a single sensor that's rated for 10,000 newtons, which is roughly 2,500 pounds, you can actually range the sensor to optimize the measurement. So if you're measuring high level forces at 10 kilonewtons one day, and the next day you're measuring 1 Newton forces, you get a reciprocal benefit of broadband noise. So the real magic of a charge amp is that it scales the measuring range and scales the noise voltage as a function of measuring range. So you actually get a reciprocal benefit. So you can see there at 1 Newton, you're at 0.0045 newtons RMS noise, whereas 10 kilonewtons, you're at about 0.6 of a Newton broadband RMS noise. So quite a good feature in terms of this technology is the rangeability. In terms of what you do, now that you have this signal and it's a voltage, you have a charge amp or you have an IEPE signal that's available, you now have to be able to sample it. And certainly there are other charge amps as well. Nowadays, charge amps like the lab amp give you not only the high-end charge amplifier with all the rangeability that we talked about, but it also gives you integrated data acquisition on top. So what that means is that in one device, you're able to do both the rangeability, the scaling, the quasi-static measurement, as well as record data upwards of 200 kilosamples per second per channel, which is quite powerful. Now, with these amplifier families, there's many ways to program them. There's certainly a firmware that's fairly intuitive. There's demo tools. There's other software called DynoWare, but fundamentally, there's also drivers for LabVIEW as well. So if you're thinking of a LabVIEW based solution, these solutions are certainly compatible with that as well. So nowadays, you have a lot of in one small box, there's a lot of capability with the digitalization of signals and being able to use software in a smart manner. You can really achieve some high-end functionality in your measurement. There's also, now the lab amp is really looking at more piezoelectric solutions. Then you have a platform called KeyDAC, which is looking at multiple measurands, multiple signal formats. And what it is able to do is really be able to interface with existing sensors that might be available, as far as what might be already on the shelf, as well as new sensors that you might very well purchase. And certainly several softwares and several different hardware configurations can also be interfaced to, whether it be a lab amp or other KeyDAC chassis, for example. So in a hydrodynamic solution, you're not just measuring force, you're measuring a multitude of signals. So the concept behind KeyDAC is really just a general platform for data acquisition that can accommodate upwards of over 20 measurands and really be a generic platform that allows you to take synchronous data in on one unit and really be able to then make some really high level decisions to see how your measurements really performed. Certainly with any platform such as this, you also need software. So the Key Studio Lab is really a platform or software that really enables you to coordinate various data acquisition measurements, whereas JBeam is a software that really allows you to analyze those measurements and really visualize, write reports, and really get to the detail of signal processing of how you're going to actually optimize your measurements for the given scenario that you're measuring. Certainly with any hardware and software packages, there are always ways of starting, really at a low level and building up, or come in at a high level, a professional package. But what you'll see is really it's good to have such choices, because some applications might not be as demanding as others. And you can see here having 2D and 3D plot capability, FFTs, filtering capabilities, as well as report generation, really is a real plus. And nowadays it's almost like a prerequisite to doing any analysis nowadays, is to have all these features available. So now that we've got a little background in piezoelectrics and software and hardware and how it all works, now how do we now take it to a point of measurement? Well, in force measurement, there are I introduced the single and three component force sensors. Now what you can do is you can actually use those sensors into what's called a force dynamometer. And what a force dynamometer is it's comprised of an array of force sensors between two thick metal plates, as you can see illustrated in this cartoon above. And what happens is force sensors on their own really like axial loads. Well, in a hydrodynamics application, you rarely have axial loads. So what happens is the plate itself helps distribute those forces amongst the sensors and basically absorb moment loads, so that you can really make an accurate measurement when your forces are not axial. Certainly with this, there's a lot of rules and a lot of rules to put together a force dynamometer. I mentioned here in terms of considerations. I'm going to go over a few of these in the next few slides, but certainly this is where, if you're thinking of making a force dynamometer from three component load cells, it's certainly great to certainly appreciate the detail here, but also just contact your favorite application engineer and see what kinds of considerations they could address for you. But in any measurement, you're always going to have analog bandwidth considerations, and with force it becomes even more critical, because with force the sensors act as spring mass systems, and as spring mass systems they're going to be influenced by mass. Okay, added mass. So when you have added mass, you're going to actually reduce the natural frequency, for example, and that'll affect your analog bandwidth. So there's always a calculation and always an FEA that has to be done when you're looking at using force sensors in any application of this of complexity, where you want to look at stiffnesses, you want to look at the geometries of the sensors, the sensor parameters themselves, and really calculate what the modes of vibration are for the platform itself, to be able to gauge what your frequency requirements are. Ultimately, you have a test article that needs a certain frequency extent to be measured, and if you can't achieve that with the fixturing that you're using, then you need to go to some other types of sensors perhaps, or another design. So it's very critical to have an FEA step in the middle of this. So I just show this picture of force sensors. These are three component force sensors, and really just to look at the terminology. Okay, I talk about things to do with sensitivity. Certainly that's pretty straightforward usually, but linearity and hysteresis are really some of the key errors in any sensor is the linearity. So we'll get into that in a minute, but linearity is a function of input versus output, and usually done at a single frequency, for example. Crosstalk is any device measuring multi-components is going to have the ability it doesn't have the ability to perfectly measure every orthogonal axis. You're going to have some crosstalk. So how well a manufacturer can do that is very critical often to the application. And certainly understanding the stiffnesses are also very critical too. You can see here from small sensors of about 10 millimeters, 19 millimeters OD on up to 150, 105 millimeters OD, you can see that the stiffness could be vary by a factor of 25 to 30, which is huge when you're looking at achieving certain frequency responses. These three component sensors would need to be preloaded, and that's why you see the hole in the middle. And there's a preload bolt that goes in there, and I'll address that shortly. There's also already preloaded versions at the factory, which have a top and bottom flange, which means that they could be simply integrated between two parallel plates very simply with very little effort. So, and they're fully calibrated instruments in their own. In terms of six component measurement, when you're getting to forces and moments, I talked about force dynamometers, and this is what one looks like inside the actual sensor itself. You see 4 3-component load cells separated by a vertical distance A from the center and a horizontal distance B. So there's a certain geometry there, and you can see the coordinate frame that I show there. You can see where the X, Y, and Z axes are, and certainly any of the moments as well. What happens in these dynamometers is actually 12 signals in this dynamometer. There's 4 3-component sensors, but we can pre-sum X and Y together. So you take 4 signals and convert them to 2 total. So what you see here on the right is actually a closed form expression for forces and moments, and which can be computed, in software, certainly by your own program, or the hardware I show you there. That charge amp actually has a summing calculator, which actually outputs 6 analog signals, plus or minus 10 volt in span, and with actually implementing those equations in hardware. So there's many ways to go about it, but it's that I'll say that technique is often used when you start measuring forces and moments in your measurements. So, multi-component basics, I talked a little about the technology, but load-bearing surfaces to make sure that you have flatness and parallelism under control. We talk about 0.01 millimeters or like a half a thou, and those are all very important. A lot of times, like a thou is probably the maximum type of flatness and parallelism I would ever recommend, but typically between 0.01 millimeters and 2.02 millimeters is typically very usable and practical. You see here on the right hand side a preload bolt. The yellow element is a preload bolt. There's a sliding, or there's a ring nut that goes on top. There's a centering sleeve, and then basically you put it in the bottom plate and tighten it to the bottom plate. So this is basically how preload works. Preload is very important for both ground isolation and shear force handling, and certainly for compressive and tensile force handling as well. All very critical. Linearity, as I mentioned, is basically the deviation of if you plot the input versus output at a constant frequency, for example, you would then fit a straight line through 0 between those points, a best fit straight line, and you would then compute the deviation from that straight line to derive the linearity. So linearity is very important in terms of having very high linearity to get the best measurement. But what often I recommend to a lot of times with these piezoelectric sensors is that you can actually have such a huge range, measuring range, and you have rangeability. So what you can always request is partial range calibration, and you can see here in the little example I gave you that the linearity actually improves as you go for smaller partial range calibration. So at a 45 kilonewton range, you're at 0.13 versus the full scale range, you're at 0.47 linearity. So you definitely get an improvement, and sometimes it's good to do some advanced work at the factory and say, hey, I want to partial range calibrate that sensor. You see, preloading also acts as a force shunt, so there'll always be, because it's in parallel with the sensor itself, so it will take up some force, somewhere between say 5 and 10%. So your actual sensitivity under preload is actually lower, which is very much expected by virtue of the stiffness of the bolt versus the stiffness of the sensor. I mentioned before tensile and compressive force measurement. That's done by preloading. If you preload to 2/3 of the measuring range, you're able to get plus or minus 1/3 compressive and tensile measurement. Force sensor alignment within a dynamometer. Every 1%, 1 degree of misalignment in X and Y is basically a 2% crosstalk in X and Y. So it's very important to have sensors lined up. And the good news is that these sensors they look round, but they actually have flats. And because they have flats, you can simply use a straight edge to align them, and it works actually quite well. Then lastly, crosstalk, as I mentioned, what's in the data sheet is often the maximum producible crosstalk, but what actually you get in the CalCert is actually quite a bit, better than what's in the data sheet. Typically, you can see here in some cases you get actually 0% crosstalk between here X and Z, which would be quite perfect actually. So there are quite a bit better crosstalk than maybe what's in the data sheet, but that's pretty common in at least Kistler data sheets. As far as the tow tank and wave tank application, this is a typical scenario where you'd use charge amps up on the carriage. Okay, you hook them up to a top and bottom plate where you have 4 sensors located in between. You have a ship model on the bottom, and then you basically run the ship model through the water, and you're measuring the forces and moments, reaction forces and moments of that event. And certainly with these systems, there's a reason for choosing each one based upon the actual loads you expect, based upon the depth that the model might be at, what type of protection is needed, IP68, for example, and then certainly what the charge amp we would use is typically for tow tank and wave tank is a quasi-static amplifier, which can measure DC as well as dynamic signals. This is just an example over the University of Michigan, who took one of our piezostar sensors. Actually, this is a 3-component force link, and they basically integrated it within a 2 parallel plates. You can see the 4 sensors are in the corner here. You can see the 4 holes that pick up these 4 holes in the flange, and basically they have a mechanism on top that they can hook onto their carriage, and they run it through this through the tow tank, which has a fairly long duration measurement for quasi-statics. You can see here that the 2 engineers here are just building this force platform into their model, and this is certainly all waterproofed IP68, and the data acquisition equipment is all on the carriage, and it's easily integrated and measuring signals very accurately and very easily with some of their LabVIEW capability there as well. In terms of submersible force, we present this picture just to show you that there are almost endless options with regard to force. Okay, you've got single component force. The cabling that we provide is welded, and that can get you down to like 16 bar or 232 psi. So it's quite well proven and tested. There's also multi-component or 6-component sensors, which can also be down to say 13 bar or 190 psi in pressure. There's 3-component sensors that you see up on the upper right-hand part, which are using removable cables, as well as weldable cables, which is a choice or is a selection, and based upon your scenario, you can choose either. They all work quite well. There's also now a submersible 3-channel charge amp, which we'll talk about shortly. And there's also submersible dynamometers, either on the shelf or off the shelf dynamometry, or things that are built up by a customer or by, say, the Kistler, custom product laboratory, which basically makes custom dynamometers. So many ways to go about it. Charge amplifiers, like I say, there's many different ways. You can go with a key DAC solution, the lab amp solutions, or even a pure analog solution, such as the 5080, all very commonly used. I just wanted to show briefly this 1698 AI and AB cable. The AI cable is an armored cable, steel braided cable. It's very much qualified for IP68 at like I say 190 psi. whereas there's a more flexible AB cable that's also qualified up to 13 bar, but you really have to take care here to make sure that your strain relieve near the connector so the cable doesn't bend too appreciably where this connector can be, say, dislodged due to, say, just poor strain relief. So you really need a good strain relief solution to use a more flexible cable. But fundamentally, they both work quite well. We've used both in tow tank applications. With this type of a solution, you're terminating to a Fisher connector, and that, by the way, needs to then go to a breakout cable that gets you to 3B and Cs, which is a fairly common approach. The submersible amplifier I talked about is basically one that could retrofit to any of the 3 or 6 component sensors that we have. There's a common connector called a V3 connector. This has several different ranges, okay, in terms of picocoulombs. So you can simply choose the right amplifier for the measuring range that you've got. There's many ways to configure it. It's customizable in terms of the length of cable, in terms of the time constant involved, but very much in terms of a lot of applications we come across. The model itself is a very small watertight compartment where you can't put electronics in there other than, the data acquisition system. So what happens is you need IP68 amplifiers, which can be totally submersed with the sensor, and in that way, it really puts a real good compromise in place where the signal conditioning and the sensor themselves are fully submersible, and the data acquisition is in the watertight compartment of the model itself. One thing I like to mention with this is that there's certainly you can look at scenarios of different sensors. And we talked about the 9017, that was the piezo sensor. And you can see here drift is actually 1/3 what you would expect from a quartz sensor, the 9027. And I showed you these sensors before. They all have certain load handling capabilities, but really sometimes it's not just load handling that you want to look at. In some cases, it's also stiffness, where you're looking at overall integrity of bending moment of your platform, and stiffness is often very critical to that. So you can see here using a 9047 could be upwards of 3 or 4 times the stiffness of the smaller sensor, and it gives you much more operational margin, not only from a measuring range standpoint for all the, say, challenges of a measurement underwater. You're getting the added margin in terms of bending moment and operational loads as well. So a lot of times it's not just the measuring range. You have to look at other parameters when you construct your force dynamometer. I talked previously about multi-component force. This is a 6-component sensor, and you see it's actually got a through hole. And it's used, you say, well, that can be used in maybe prop shaft measurement. Well, not quite yet. Okay, it's a charge mode output. Yes, it could use the inline 3-component amplifiers I just showed you before. But there's also already packaged prop shaft sensors that are 6-component that can measure forces and moments as well. So they're completely balanced so that you have a very much a proper solution for a rotating shaft, which is very cool. So that's of interest. Definitely contact your favorite application engineer to talk about prop shaft measurements. As far as dynamometers, there's simple rules involved. Certainly, this is a kit that you can use to make your dynamometer. It's rated down to maybe, I don't know, 5 bar or so, which is plenty good for a lot of tow tank applications. But what you do is you can make your own top and bottom plate, your own geometry, and then certainly save a lot of cost in terms of doing that. And that's one of the things that's very attractive to some customers, is that they like to be able to, maybe have a modularity that they can construct different dynamometers based upon their needs. So a lot of times that could very well do the job. Certainly an application here where you have a flume and some coastal, some model that acts, to model a coastal structure, you can use such a kit to really measure these forces, certainly. And that's a real common application where you get the quasi-static and dynamic measurement capability. In terms of the dynamometer, I mentioned before, it's a spring mass system, so adding mass is going to affect natural frequency. This is pretty much pretty straightforward to all of us who are familiar with this spring mass equation. The more mass, the less frequency or operational frequency you get. So you always have to take that into consideration. And certainly when you mount dynamometers, you always want to mount with the stiffest arrangement possible to get the best frequency response possible as well. You can see here with the blue curve, you get a very smooth resonance characteristic, and you get the highest resonant characteristic than just mounting it with 4 bolts. You're mounting it with many points. This is absolutely the best way to get the best frequency response. And calibration, of course, when you're doing your own dynamometry, you always want to do calibration. Well, in this case, this is a factory calibration where you'd have, a multi-component force rig that's applying known forces on the sensor itself. There's a strain gauge load cell in the path, which measures the actual applied force, and there's a piezoelectric force sensor in there to do the actual calibration, which is pretty common. Other technologies in force is certainly bonded foil strain gauge. We talked about piezoelectrics, where you basically have a very stiff sensor made of quartz and metal, and you're relying upon the forces or the loads on that piezoelectric material, which would be proportional to the measured force. In terms of bonded foil strain gauges, you're using a flexure element, some device that flexes, and you're using a change of resistance, which is proportional to the load. So it's a totally different concept. But what happens is in strain gauge, you're able to measure pure DC, pure static load measurements. So it's absolutely quite optimal for that. I'm often asked, hey, how do you compare PE versus strain gauge? And I'll tell you, there's a multitude of ways to do it. I took a shot at it here just to give an idea of what are the pros and cons. But by all means, it's always application dependent. And like I always say, call your favorite application engineer, because a lot of times it's the devil is in the detail. Is whatever your application is, we can dial you into what the best technology might be. For sure, piezoelectric is optimized for rangeability, like I said, for high frequency, and does have quasi-static. And strain gauge is optimized for static and does have some dynamic, and certainly has a very good compensation with temperature compared to piezoelectric, for example. Some of the feedback I get from strain gauge users and piezoelectric users, and some of them use both, but they really like the natural frequency capability of the piezoelectrics, the fast response time, and the adaptivity of the platform. Because you have modular elements that are all pre-calibrated, you can easily create different structures, triangular arrangements, rectangular, square arrangements of sensors, and really achieve a known solution. And in very little time, you can have the platform built up and tested and calibrated in situ, and taking measurements straight away. So there's a lot of feedback I got was along the lines of just ease of use, and just the response and the natural frequencies were quite favorable to what they wanted to do. So in terms of a checklist for force, I mean, there's quite a few different things to consider. Like I said, I mean, to make everyone an expert in the matter of maybe an hour is a little bit high of an expectation, but just to create an awareness that says, hey, look, everyone, if you're getting into these types of applications, please, certainly, call your favorite application engineer and chat with that person, and really, get the best advice. But you need to consider these types of parameters for sure. So segueing to pressure, there's in terms of pressure, there's piezoelectric pressure. Working principles, as I said before, are very similar. You've got a quartz technology usually, and you're stressing that quartz, and that output is then proportional to pressure. And in terms of that, you've got piezoelectric and IEPE. All the same rules apply, that I mentioned before for force. They all apply to piezoelectric and IEPE. A lot of times with a hydrodynamic solutions, the charge mode configuration is used more, but there are causes to use the IEPE as well. But again, it's application dependent. So with piezoelectric, as I mentioned, the resistance change of resistance is proportional to pressure, And this is all very, very basic. And a lot of times it might even be that the Wheatstone Bridge or the resistance bridge is actually, in an oil reservoir, which actually also provides very good, media separation, and any thermal effects tend to be mitigated by virtue of the oil-filled capsules, for example. So with piezo-resistive sensors, some of the technologies, silicon-based technologies, which are oil-filled, have very high burst pressures, very high gauge factors compared to traditional strain gauge, bonded foil strain gauge. So I would say, even though something is called strain gauge or piezo-resistive, really take a close look at the parameters themselves, because a lot of these really help the measurement. Because, there's always, in my experience with measurement, you can always have a bad day. Okay, so having resistance, 4 times the full scale for burst pressure of an overload capacity, is very cool. With strain gauge, bonded foil strain gauge is, it could often be less than that, or you have to make some compromises to get, high overload capacity, such as picking a very high range and really suffering in resolution, for example, might be one of the trade-offs. So with piezoelectric and piezoresistive anyway, you get very high resistance to overload conditions. With regard to piezoelectric solutions, I talked previously, dynamic pressure optimized as well as quasi-static pulsations, pressure pulsations, as well as dynamic, say, transient pressure events, are all very nicely measured by piezoelectric. Wave impacts, for example, would be a typical, transient event that you would find that a pressure sensor might be used. In terms of piezoresistive, you certainly have the dynamic or transient events, as well as the low bandwidth pulsation events as well. Static pressure as well is absolutely optimized for piezoelectric measurement. So if that's part of the requirements, there's certainly that technology will best suit that measurement. In terms of the checklist, no shortage of parameters to think about, but certainly when you talk to your favorite application engineer, these are the considerations we'll often ask about, and we'll say, if we can, get a gauge of what your application is in terms of these parameters, we can often guide you to the best solution. In terms of submersibility of this technology, certainly the piezoelectric and IEPE has a welded cable solution, which can basically get down to 16 bar or 232 psi capability. So it's all IP68 rated. A lot of times with this type of technology, well, the 601C is one of the sensors, and it can measure upwards of 3,000 psi plus, or 250 bar. And certainly the IEPE versions have individual ranges for each, as I mentioned, because it has an internal electronics, it needs to have a fixed range. So you often see many different ranges covered. Small dimensions, the diaphragm is only 1/4 inch or 5 millimeters. Fast rise times and low thermal shock would be very key. And the 603 is an acceleration compensated version, similar type of construction, similar size, but certainly optimized for, say, more high bandwidth type of events. One of the typical applications we see is wave impact and slamming. And a lot of times with these types of piezoelectric sensors, you can get very small. Like I said, the diaphragm is just 1/4 inch or 5 millimeters or so, 5 to 6 millimeters. And what you're able to do is tightly pack the sensors together to get very good spatial resolution of the impact. And you can see here in this tank here, the waves forming and hitting a structure at the end. And this structure would be one that would be comprised of these various sensors themselves. The small piezoelectric sensors, that is. And this is a typical impact profile that you would see, a very short duration impact where it comes back down to zero after the impact. As far as submersible sensors, the piezoelectrics are well represented, but there's also the piezoresistive yet are not submersible at this time, but certainly something in the future is certainly on the roadmap and might be something we can do later on. Just consult Kistler if that's a consideration. As far as other pressure applications and other general applications, cavitation tunnel testing is often performed, and you can see here definitely pressure level events here in the cavitation tunnel, where you can see the black curve is with cavitation, where you see elevated pressure ranges versus the without cavitation lower pressure ranges. Very common. But in these types of scenarios, what you're doing is you're able to model more higher with a single, say, scale model. You're able to actually, test it over, higher loads than what you would do in air. And that's the combination of pressure and water really allows you to do that. So there's all kinds of different tests that are performed. It could be a torque and thrust test. It could be vibration or cavitation, pressure distributions and disturbances, as well as just laminar flow, steady and unsteady forces or flow conditions. In terms of sloshing, there's for the liquid natural gas industry, there's a lot of research done in ship stability and certainly how to ensure ship safety in high sea state with liquids sloshing around in these tanks. And certainly each tank might have baffles to damp out the isolations as well. Very important application. Certainly in the industry, they're using these hexapods to simulate the various ship motion. And in this hexapod, on the side of the hexapod plexiglass frame, there would be this high density pressure sensor array that can measure, like I say, spatially resolve these wave impacts very accurately and very thoroughly with just a simple pressure sensor. And picking the right pressure sensor will actually also give very good performance with thermal transient response, because when you have air and water, they're not necessarily at the same temperature, and even a few degree temperature difference could result into substantial errors. So having a measurement like the 601C that I mentioned, which is has a special diaphragm that's optimized for thermal transient response, really helps in taking such measurements. Then there's also rave crash walls, which are basically same type of platform where you have a highly or tightly spaced pressure sensor array into a closed vessel with pressure, temperature, and water effects. So you're able to characterize that as well with a 601C, with a lab amp as the data acquisition system, where all channels are synchronized using PTP or IEEE 1588 type synchronization features in the measurement. Then lastly, acceleration. I'm closing on my allotted time, but vibration and shock and acceleration are all similar terminologies. Acceleration basically includes, I'll say, DC components as well as AC components. Vibration is purely a continuous AC coupled event, dynamic event, and where shock is a short duration transient event. So those all can be measured with an accelerometer. Accelerometers also have the PE and IEPE formats, all much along the same lines as what I mentioned before: rangeability, quasi-static capability, and certainly many of the accelerometers we come across are IEPE nowadays. And this is probably most used in terms of hydrodynamic measurements. There's also MEMS capacitive. MEMS is a micro electromechanical structure, and this structure is basically illustrated here in this model, where you have basically a spring mass on a cantilever beam that's suspended, and you have a top and bottom electrode, and how that spring mass moves between these two electrodes dictates the differential capacitance. That differential capacitance is absolutely directly proportional to acceleration. Now you say, gosh, I don't know anything about capacitance or anything to do with capacitors. Well, you don't need to, because the factory actually worries about that. You basically get an accelerometer that's calibrated millivolts per G, and you just have to put it in your application. And you don't have to know anything about a capacitance or a picofarad at all to use this sensor. Works fairly nicely, and it gives you the DC response as well. Okay, unlike piezoelectric, like I mentioned, which is AC coupled, you're going to basically get a DC coupled and dynamic sensor, which measures both types of signals. The frequency response of a piezoelectric, again, is a lightly damped second order system, whereas with a variable capacitance or MEMS capacitive accelerometer, it's basically a near critically damped second order system that has a very well behaved second order response. You can see here has DC response with about a 20 dB per decade roll off. Yeah, as far as the accelerometer review, yeah, there's piezoelectric by far has the widest ranges, but again, I think for dynamic measurement, it's very much quite optimal, very small, very compact. Whereas MEMS capacitive is a little bigger, but it gives you the ship motion type of ability to measure ship motion or small amplitude waves. So a low frequency wave motion would be best measured with a MEMS capacitive accelerometer since it has 0 hertz capability. As far as underwater solutions, these 3-axis sensors are all qualified IP68 for 145 psi pressure, all tested at the end of line for that, so they're all coming with a certificate stating that. There's also various ranges from 50G on up to 2000G. Very small sensor, upwards of 0.4 of an inch, or say 10 or 11 millimeters cubed. There's also a single axis version, which sometimes is a nice cost saver, and it also has waterproofed or IP68 cabling, which is also rated for 10 bar or 145 psi as well. Certainly, these sensors occupy 50G on up to 500G and are very flexible and give you the IEPE signal format, and very much a dynamic sensor. Not really useful for measuring low frequencies below, say, 1 hertz, 1 to 2 hertz. The triaxial version of the MEMS sensor is coming with a integral cable IP68, also rated for 10 bar, and they come in 2, 10, 30, and up to 200G ranges. It's a very useful technology, for hydrodynamics, where you want to measure low frequency structural vibration, or maybe even wave effects, low frequency wave effects. As a true DC response sensor, it's absolutely optimal for those measurements. And again, the overview, many different types of signal formats or accelerometer formats, from single axis to triaxial, piezoelectric, IEPE, as well as MEMS 3-component sensors are all available, depending on the application. Just an illustration of what you see here is certainly in terms of the sensors themselves and what type of signal conditioning might be available. But all the solutions are IP68 shown here, all very much proven and tested at the end of line. And lastly, there's an accelerometer selection test consideration list, much like we had for pressure and force. So again, to make everyone an expert in 1 hour is just not a real achievable expectation. But what we hope to do here was really just increase the awareness of what to ask, what to look for, and certainly talking to a capable application engineer will give you the best insight and recommendations into your application. So, as an application summary, we covered a lot of ground here in not quite an hour. Certainly from tow tanks to wave basins and slamming, sloshing, prop shaft and propeller cavitation, flow-induced vibration, as well as structural dynamics testing, all with accelerometers, force sensors, pressure sensors. A lot of customized solutions available, a lot of solutions available that are already IP68 qualified for, I'll say, the demanding environments of test for sure. So on that side, I'd like to ask if there's, give it back to Pascal and ask if there's any questions.
Yeah, many thanks for that, Bill. It's a really comprehensive overview. I really learned a lot, and I'm pretty sure that all the other guys also learned a lot during this 1 hour. Yeah, there were some questions, and the first one was, what is the typical natural frequency of a dynamometer?
Typical natural frequencies of dynamometers will be range between, say, 2 kilohertz and maybe 5 kilohertz, and it depends on what axis. But I'd say somewhere between 2 and 5 kilohertz would be a typical value to think about. And again, you always have to factor in any mass loading into that, but the amount of mass you're gonna add to it will affect the overall frequency response, and certainly the size of the platform too. The smaller the dynamometer, the higher the natural frequency, typically.
Many thanks for that. Then other one. So are there any other possibilities to detect cavitation? For example, if you're on a ship, so they do not want to mount a pressure sensor in the bow of the ship.
Yeah, there's a technology called acoustic emission, and it basically uses ultrasonics involved, and it's actually been used quite successfully in water cavitation for either pumps or even water turbines. So I would say the acoustic emission technology would be one, perhaps even an accelerometer to some degree, but it's definitely proven that acoustic emission sensors would be a good candidate to consider. And I would say if you have any questions on that, certainly get in contact with your local application engineer or local sales engineer, and we certainly will help you in every way to brief you on this technology. We didn't address it in this presentation, but certainly it's something we can talk directly to you on if you're interested. Let us know.
Yeah, many thanks for that. Let's come to the last question. So, what is the longest cable these sensors can work with?
It varies. So between say 20 meters and maybe upwards of 100 meters of cable, but it really depends on the sensor, and it's more of a producibility question. And also, for low signal levels, we like to keep the cables on the lower side. So I'd say typically 20 meters would be a typical answer to give you, but we can go longer depending on the application.
Yeah, so we hope we answered all your questions. If there are any left, then please feel free to contact your local sales, to contact Bill or me. So we'll be really happy to answer your question. And we are also happy that you joined this webinar. So this one was recorded, as mentioned at the very beginning, and we will share the link so you can rewatch it. And with that, we wish you a good day and speak to you soon. Bye-bye, guys.